Hello, welcome to another module in this massive open online course. So, we are looking at an additive white Gaussian noise channel, which is which we have said is the simplest one of the simplest models that can be used to represent a digital communication system or a digital communication channel, or the effect of channel or which can be used to model the effect of the channel in a digital communication system. And we have said in that we have looked at a simple system in which yt, the received signal yt, is simply the transmitted signal xt plus the noise. So, the noise is adding to the transmitted signal xt, this is termed as additive noise. Alright, we have already seen that the noise, this noise which adds to the signal is termed as additive noise. Now, the other important property, the other type of noise, which is one of the most popular noise models in a typical communication system, is to consider Gaussian noise, that is noise NT, noise process NT, that is noise NT, which is random and which is a function of time, therefore, it is a random process. So, noise, this is random plus it is a function of time implies this is a random process, correct. Now, another very popular model for noise is to consider this noise process NT as a Gaussian random process. So, another very popular model, since most naturally occurring random processes are Gaussian. So, a popular noise model is a Gaussian noise, or basically a Gaussian noise process, which basically means it is a noise is a random process. Okay. So, this noise Gaussian noise basically means the noise is a Gaussian random process, alright. So, this implies noise is a Gaussian random process. Now, we are going to see the properties of the Gaussian random process. So, this means that your noise is a Gaussian random process. Now, what is the meaning of this Gaussian random process? Random process, we call a random process as a Gaussian random process. Now, let us characterize a Gaussian random process. Let us characterize a Gaussian random process. Now, we call a random process NT is Gaussian, NT is a Gaussian random process if the joint statistics of, if the statistics of all orders are jointly Gaussian, is Gaussian random process if statistics of, and this is important, statistics of all orders, not just a single order, statistics of all orders if statistics of all orders are jointly Gaussian. This implies, this means this basically means, that is, if you look at noise samples NT1, that is if you consider noise samples NT1, NT2 up to n Tk, these are basically, you can see these are k noise samples. Okay. these are k noise samples at times t1. That is what we are basically doing is we are taking this noise process nt and we are considering k noise samples at time instance t1, t2 up to tk. These noise samples are given as nt1, nt2 up to ntk. And you look at, if you look at the joint distribution of these now k noise samples, okay, if you look at the joint distribution of the k noise samples, let us denote this by f of nt1 comma nt2 comma so on ntk n1 n2 up to nk. Okay. This is the joint distribution of the noise samples. Now, if this joint distribution of noise samples, if this is jointly Gaussian, all right, this means it has a multivariate Gaussian density. If this is similar to the scalar Gaussian density, there is a multivariate Gaussian density, that is considering multiple random variables, that is follows a multivariate Gaussian density, and this has to be true for not any particular correction, follows the multivariate Gaussian density for all choices of T1, T2, Tk, and more importantly, and also not more importantly, also for all k, that is if you choose any k points, if this follows, if there are nt1, nt2, ntk for all such noise samples, all such combinations of k noise samples and for all values of k, if this follows a Gaussian density, then it is termed as a Gaussian, then as a Gaussian then it is termed as a Gaussian random process, or basically also your noise is a Gaussian. If it is a Gaussian random process, noise plus Gaussian random process implies, that is noise plus not Gaussian, not simply Gaussian, but a Gaussian random process, noise plus your Gaussian random process is basically your noise which follows a Gaussian random process is termed as a Gaussian noise. So, as you can see, we term noise as Gaussian. Basically, if you the statistics of all orders are jointly Gaussian, what that means is, if you look at the noise process NT, consider k samples at T1, T2, Tk, NT1, NT2 up to NTk. If the joint density, probability density function, all right, of NT1, NT2, NTk is Gaussian, that is it is jointly Gaussian for all such samples, that is for all such instants T1, T2, Tk, and for any possible value of k, all right, that is also important. It is not fixed, it should not be it is not for a particular value of k, but for any such value of k, that is for k equal to 1, k equal to 5, k equal to 10 or 1000, that is if you take 1000 noise samples and the samples are arbitrarily chosen time instants, all right, the joint probability density function should be a multivariate, should be Gaussian, that is it should follow a multivariate Gaussian density. alright, and then such a random process is known as a Gaussian random process. In particular, if the noise, correct, if the noise is a Gaussian random process, alright, it is known as Gaussian noise, alright. That is, and this, as we have said, is one of the most popular models, alright, because most naturally occurring probability random variables follow the Gaussian distribution, or we can also say that the most naturally occurring random processes are Gaussian random process. Therefore, the Gaussian noise, alright, to model this thermal noise, the circuits, alright, the thermal noise in these circuits in this at the receiver, alright, which arises from basically from the thermal noise in the circuits at the receiver, is modeled as a Gaussian random process, and this is one of the most popular models, popular noise models for a digital communication system. Okay. And this is employed almost throughout, that is, if you look at literature on digital communication, a dominant fraction of literature would employ the Gaussian noise process. Okay. Now, in particular, the Gaussian noise process is a very interesting property. Gaussian noise process if a Gaussian noise process is wide sense stationary, if it is WSS, that is if a Gaussian noise process is wide sense stationary, then it implies it is also strict sense stationary. No, normally this is not true for a random process. Wide sense stationary random process, that is a strict sense stationary process, alright, is a much more rigorous condition, alright. So, strict sense stationary processes are all strict sense stationary processes are a wide sense stationary, but the other way around is not true, that is all wide sense stationary processes are not strict sense stationary, alright. So, strict sense stationary processes are a strict subset of wide sense stationary processes. So, if you look at the set of random processes, correct, correct, if you look at the set of random processes, then there are several random processes that are wide sense stationary, but only a few of them are strict sense stationary. So, typically if it is strict sense stationary, it implies wide sense stationary. Typically, wide sense stationarity does not, because wide sense stationarity is a much more relaxed condition. So, typically wide sense stationarity does not imply strict sense stationary. However, for a Gaussian random process, wide sense stationarity implies, that is the interesting point. For a Gaussian, only for a Gaussian random process, only for a Gaussian random process wide sense stationarity implies, but this is important to realize that only this happens only for a Gaussian random process, not for any general random process, only for the specific case of a Gaussian random process, a wide sense stationary, that is, if a Gaussian random process is wide sense stationary, then it is also strict sense stationary. And you can briefly revise, alright, we can briefly see what are the conditions for wide sense stationarity. A random process is wide sense stationary, that is NT is wide sense stationary if, well, expected value of NT equals mu for all t, that is the mean is constant, and expected value of NT, that is the correlation or the cross correlation between two time instants t and t plus tau, the correlation depends only on R Nn of tau, once again for all t comma tau. For all t comma tau, this depends only on tau. You can see that the correlation between Nt and Nt plus tau depends only on the time difference tau. Okay. So, these are the conditions for wide sense stationarity. Okay. So, these are the conditions for wide sense stationarity. And for a Gaussian random process, what we have shown is that if these conditions are satisfied, if the Gaussian random process or the Gaussian noise process is wide sense stationary, then it is also strict sense stationary. But have to keep in, one has to keep in mind that this is only for a special random process, that is if the random process is Gaussian. Okay. Now, let us look at the other property. So, we have seen additive. So, we have seen the following properties. We have seen the noise, the additive property of the noise, Gaussian property, when is the noise Gaussian. Now, we are going to see a different property, which is the whiteness, or when do we call noise as white noise. So, we have to see the property of white noise. So, the other important thing is property of noise is white noise. Now, this property is motivated by the following observation: noise typically has very low correlation, that is temporal correlation. If you look at the correlation, that is if you look at a noise process, then the noise process looks something which is very erratic, very erratic, something that is unpredictable. I mean, if I have to draw it, let me just draw it appropriately. That is the whole point. The noise process is very erratic. So, noise process is very erratic. It has very low temporal correlation, unlike a signal which is very smooth. For instance, if you look at a signal which is smooth, so you have a noise process which is very erratic, and the signal, typical signal which is very smooth because it has a high level of temporal correlation. This has a high level of temporal correlation or correlation in highly correlated in time. On the other hand, noise has very low correlation, across time. Noise has very low Noise has very low correlation across time, alright, and the signal, the typical signal has is smooth, it has a very high level of temporal correlation. So, one way to model this very low temporal correlation is noise is to model the correlation, that is if you look at any two time instants, expected value of nt into nt plus tau equals eta by 2 times delta tau, and this looks like, that is if you look at the correlation between this quantity is nothing but expected value of nt into nt plus tau, this is the correlation between nt and nt plus tau. We are saying that this correlation between nt and nt plus tau is eta by 2 times delta tau, which means it looks something like this. This is the axis, this is tau and this is r nn of tau, that is if we plot this correlation r nn of tau. Now, this correlation is simply an impulse function scaled by, this is simply an impulse function, that is it is simply, that is if you look at this correlation, it is simply an impulse scaled by eta by 2. Impulse scaled by eta by 2. So, this is simply an impulse scaled by eta by 2, which means if at tau is not 0, this is 0, you can observe that delta tau, correct, delta tau equal to 0 if tau not equal to 0, which implies at all these points, that is tau not equal to 0, correlation is 0, that is noise that is if you look at this expected value nt, that is if you look at this correlation expected value of nt plus tau, this is equal to 0 if tau is not equal to 0. What this is saying is, if you look at any two different time instants t and t plus tau, that is t and t separated by a small time difference tau, the noise samples at these two instants are uncorrelated. And of course, further we are not saying it is independent, if the noise process is Gaussian then they are also independent, but anyway at this point for any general noise process which is white, alright, if the noise samples expected value of nt plus tau, noise samples at two different instants, any two different instants nt and nt plus tau is 0, that is they are uncorrelated. Such a noise is known as white noise, that is expected value of nt into nt plus tau is eta by 2 times delta tau, alright. If tau equal to 0, it is delta 0, alright, eta by 2 times delta 0. If tau is not 0, then it is 0, alright. So, the noise correlation is given by the temporal correlation, or you can look at the autocorrelation function of the noise is given by eta by 2 times delta tau. Such a noise is termed as white noise. This is termed as white noise. Which means that noise at any two different time instant, noise samples at any two different time instants are uncorrelated. the key operative word here is different, any two different time instants. T comma t plus tau are uncorrelated, and it is known as white noise because if you look at the power spectral density, remember we have R n and tau equals eta by 2 times delta tau. If you take the Fourier transform of this, then you get the power spectral density, that is S n n of f, and that is basically the Fourier transform of eta by 2 delta tau, and the Fourier transform of delta tau is nothing but unity. So, S n n by 2 f is eta by 2 simply, for all frequency it is simply eta by 2. So, therefore, if you look at the power spectral density, remember this R n and tau, this is the autocorrelation function. S n n f, this is the power spectral density, this is the power spectral density, that is the PSD, and if you look at the PSD of white noise is simply eta by 2, that is if you look at the PSD is simply eta by 2, that is it is uniform, that is it is a uniform power spread over all frequencies, that is power, the power spectral density is flat. Therefore, power is spread uniformly over all frequencies. Okay. So, similar to white light, which has power spread uniformly over all frequency components, all visible light frequency components, alright, the power spectral density you observe for white noise has a power that is distributed. Remember we said the power spectral density characterizes the distribution of power of a random process in the frequency domain. So, therefore, for a white for this power spectral density, which is proportional to delta tau, if you take the Fourier transform of delta tau is 1. So, Fourier transform of eta by 2 times delta tau is simply eta by 2. So, therefore, the power spectral density is flat over the entire frequency domain, which means that the power is spread equally over all the frequency components from minus infinity to infinity. Hence, this is termed as white light, since it is similar, its behavior or its power spectral density is power distribution across the frequency is similar to that of white light, which has uniform frequency, uniform distribution of power across all components, alright, in the all components in the visible light spectrum. Okay. So, this is basically, so power, we see PSD is flat, power is uniformly distributed. So, you see the PSD is flat, power is uniformly distributed, over all frequency components. Similar to white light. Remember, white is a combination of all the colors, so it has implies this is such a noise is, hence this is termed as similar to white light, hence termed as white noise, hence termed as white noise. The PSD, which is flat over the frequency domain, hence termed as white noise. hence termed as white noise. Okay, this is termed as white noise, that is the whole point. Okay. Therefore, now we can say that the noise process, now we have seen the three properties additive, Gaussian and white. So, now we can say noise which is additive. Now, these are the three different components, and notice that none implies the other. Noise which is additive plus Gaussian plus white, that is noise which is additive plus Gaussian plus white. If the noise is three different things, satisfy these three different properties, then the noise is additive. If only then the noise is additive, white, Gaussian, and further realize that all these three conditions are very different, none of them implies the other, or no subset of them implies the other. For instance, the noise additive does not imply it is white or Gaussian, noise is white does not necessarily mean the noise is Gaussian, noise is Gaussian does not mean that the noise is white. So, all these three components are independent, all these three different properties are separate, all right, none of them implies the other. So, only if the noise satisfies these three separate criteria, that is if it is additive, it is white and it is Gaussian, such a noise is known as additive white Gaussian. Such a channel is known as an additive white Gaussian noise channel. So, now we go back to our digital communication channel model, this channel model where y equal to x plus n. Remember, we have looked at this channel model y equal to x plus n, all right, where we have y t equals x t plus n t. Such a channel is known as an additive white Gaussian. Let me just quickly draw a simple schematic. This is a very simple yet a very powerful channel model which can be used to characterize a general digital communication channel. So, we have the transmitted signal. So, it is a very simple channel model, as you can see. I have the transmitted signal x t, I have additive noise. So, I have additive noise N t and I have this thing. So, signal plus noise, noise is additive. If the noise if N t is white and Gaussian, and of course, you can see from the figure that the noise is additive, implies it is an AWGN noise is additive and Gaussian, it is an AWGN channel. AWGN channel implies that you have an additive noise, AWGN channel implies that basically noise is additive. Again, I am reiterating the same thing because it is important. Plus white plus Gaussian. So, one of the most popular models as well as one of the most practically applicable models. Plus, you can also say that practically applicable for a digital communication system. Practically applicable for a plus also practically applicable for a digital, one of the most popular models plus also practically applicable for a digital communication system. So, basically that summarizes the AWGN noise AWGN channel model, which is basically a transmitted signal xt, your noise nt is additive. In addition, if the noise nt is white and Gaussian, alright. So, the noise nt is additive, so xt plus nt, it is a very simple model, xt signal, transmitted signal plus noise nt gives rise to that received signal yt. In addition, so the noise is additive, in addition if the noise is white and Gaussian, this is known as an additive white Gaussian noise channel, one of the most simplest, one of the most frequently used and one of the most popular and also one of the most practically applicable channel models, alright, or models for a typical digital communication system. Alright. So, we will stop here, and based on this model we will analyze the performance, look at optimal schemes for the digital communication system, for a digital communication system and also their performance in the subsequent modules. Thank you very much.